Good morning. Welcome to Lecture 5. Today we are going to discuss reflection at spherical surfaces. So we will begin with a convex mirror. So if I have a convex mirror, our goal is to see where the image would form and establish a relationship between the object distance, the image distance, and the radius of curvature. Ideally, to know where the image is, you would need to see where all the reflected rays intersect, or to see where all the reflected rays are coming from, and then that would give you where the image is. We just need to draw two rays, and looking at where those two rays are intersecting, we would know where the image is going to form. So we're going to begin with a point object. So if I have a point object at O, the nearest point between the point object and the mirror is the vertex, which we will call V. So a ray that is going straight from O to V is reflected right back along the same direction. So if I were to extend it beyond the mirror, so if I extend it behind the mirror, it's just a straight line. Now, if I look at another ray that is going from point O, object O, and hitting the mirror at, say, some point P, and so then it is going to be reflected something like that. So then I can extend this, and this is where the image would form, right? So this ray is going like that, and it gets reflected, and that's where the image would form. So notice that if I stand in front of the mirror, if I were to stand here and look at the rays, you see that this ray is going this way, and this ray is going here, right? So they're actually not converging in reality, they're diverging, but we would perceive these diverging rays as if they are coming from an object that is situated behind the mirror. So in this case, the object is a the image is a virtual image. Recall the difference between virtual and real images, and also recall the sign conventions. Notice that we are looking at light going from left to right here, as we had established in our sign conventions, right? So now, using these rays, we can determine the relationship between the object distance. The object distance would be the distance between O and V, which we will call as S, and the image distance between V and I, which we will call S prime, and the radius of curvature is simply the radius here, that is the radius of curvature. So our goal is to establish a relationship between S, S prime, and R, and to do this we will use what is called the small angle approximation. For small angles, sine x, for example, can be expanded out as x minus x cubed by 3 factorial plus x pi by 5 factorial, so on and so forth. That's the polynomial expansion, and you can see that the powers are odd. So that's the odd nature of sine, whereas a cosine is even. So you would have something like 1 minus x squared by 2 factorial plus x to the power 4 factorial, so on and so forth. So for small angles, these higher powers are neglected. So then we would have, for small angles, sine x is almost equal to x, and cosine x is almost equal to 1. And given that we define tangent as sine by cosine, for small angles, tangent of x is almost equal to sine x, which is almost equal to x, right? So that's what we are going to do. We are going to use the small angle approximation to look at relationship between S, S prime, and R, object, image distance, and the radius of curvature. So now here is the figure from your textbook. It's just essentially what we had seen on the previous slide, and it looks better because the distances and the angles are more visible here. So we have one ray going from O to V, right? It's going this way and it is reflected right back, and another ray going from O to P, and we're going to consider that it is going out at an angle of alpha, and that hits the mirror at an angle theta. That's the angle of incidence. So it is reflected at the same angle theta, and that's where we have the reflected ray, and these two reflected rays are intersecting at I. And we can extend out this radius of curvature to the center of the mirror, right? So I can think of this as a sphere, right? And that's the center, and so that's the radius of curvature between point P and point C. So now let's look at the triangle OPC. Let's look at triangle OPC, and you see that one of the angles is alpha in triangle OPC. One of the angles is alpha, another angle is phi, and let's call this angle as y. So then we know that because this is a Euclidean triangle, y plus alpha plus phi is equal to 180 degrees. If it's a non-Euclidean triangle, then you need not have sum of angles is equal to 180 degrees. But in a Euclidean triangle, the angles, the sum of the angles equals 180 degrees. So y plus alpha plus phi is equal to 180 degrees. Now let's look at the line PC. So if I look at the line PC, this total angle shown in blue should be 180 degrees, but that is equal to y. This is y and this is theta. So y plus theta is equal to 180 degrees, or y is 180 minus theta. So if I plug this back in here, then I would have 180 minus theta plus alpha plus phi is equal to 180. These two things cancel, or I would get theta is equal to alpha plus phi. Right? Theta is equal to alpha plus phi. So similarly, we can, so let me rewrite that. So we got a theta sorry about that. We have theta is equal to alpha plus phi from what we have just seen, right? Now similarly, you can see that these two angles, if I combine these two angles, I have 2 theta here, right? And if I look at this entire angle here, that should be 180 degrees. So if I call this angle as say Z, then I have Z plus 2 theta is equal to 180 degrees, or Z is 180 minus 2 theta, right? And now if I look at the triangle OPI, so OPI, then I have alpha, alpha prime and Z as the angles. So I have alpha plus alpha prime plus Z is equal to 180 degrees. Or if I plug this in here, then I would have alpha plus alpha prime plus 180 minus 2 theta is equal to 180. This cancels out, or I would get alpha plus alpha prime is equal to 2 theta, right? So essentially we got this by looking at triangle OPC, and this by looking at triangle OPI, right? So we derive these two relationships now, and let's see what we can do with these two relationships. I will clear the board and rewrite them again. So we derive these two relationships. Theta is equal to alpha plus phi, and 2 theta is equal to alpha plus alpha prime. And using these two, you can see that we can remove theta out of the picture right? So if I were to multiply this equation by 2, I would get 2 alpha and 2 phi, and if I subtracted them out, this would give me 0. 2 alpha minus alpha is alpha, right? And here I have so I'm subtracting it, so I have minus alpha prime plus 2 phi, and this is 0. So I would have alpha minus alpha prime is equal to minus 2 phi, right? Again, we got the first equation from triangle OPC, the second equation from triangle OPI. We combine those two equations to get essentially this equation. Alpha minus alpha prime is equal to minus 2 phi. Now, remember what we talked about small angles. For small angles, sine x, is almost equal to x, which is almost equal to tangent x. So if I drop a perpendicular from point P to the horizontal line OC, so I'm drawing the perpendicular and I'm calling that as H. So for small angles, I can write alpha as tangent alpha, right? For small angles, alpha as tangent alpha, which would be the opposite side, which is H, divided by the adjacent side, which is S. So instead of alpha, I'm going to write H by S. Similarly, for alpha prime, I'm going to write alpha prime as tangent alpha prime for small angles, which is equal to the opposite side, which is H, divided by the adjacent side, S prime. Notice that here we are making another approximation. We are making an approximation that VQ, this distance VQ, is much smaller than QI, that is this distance. So by making that assumption, we are writing the adjacent side for angle alpha prime as S prime, the adjacent side for alpha prime as S prime, because we are assuming that VQ, this is not theta, VQ is much less than QI, and that's how we are able to make this approximation. So there are two approximations there. The first approximation is that we are treating alpha as the tangent of it, and then the second approximation we are making is VQ is much smaller than QI. So bear that in mind. So this, whatever we have, is not an exact relationship. What we have is an approximate relationship. That's why this is often called first order optics, or because this was introduced by Gauss, it's also called Gaussian optics. We're making approximations. We are valid only up to the first order in the expansion of sine and cosine, and that's why this is first order optics. Anyway, coming back, alpha is equal to H by S, and alpha prime is H by S prime. Similarly, I can look at for angle phi. For angle phi, I'm going to look at the tangent, the sine. So the opposite side is H, right? Sine x is equal to tan x for small angles. So I'm looking at the tan sine part of phi. Sine phi is going to be opposite side, which is H, divided by the hypotenuse, which is R. So this is going to be 2 minus 2H by R. Now I can pull out the H's all throughout, and I would get 1 over S minus 1 over S prime is equal to minus 2 by R. So this is what we set out to do. We set out to establish a relationship between the object distance S, the image distance S prime, and the radius of curvature R. So that's what we were able to successfully do. 1 over S minus 1 over S prime is equal to minus 2 by R, right? But this is for a convex mirror. Now, if you want to do the same for a concave mirror, we just need to use the sign conventions that we had established. Recall that in our sign conventions, light propagates from left to right. And the second thing is that the distances, if it's a virtual image,